Hello everyone, in this video we will continue to talk about false position method. We will focus on how to implement false position method in MATLAB to find the root of a nonlinear equation. So let's see this example 2. Consider finding the root of fx, which is equal to x to the power of 10 minus 1. We start with the interval from 0 to 1.3. And we know that the root will be 1, right? So assume that epsilon step is equal to epsilon abs, and both of them are equal to 1e negative 3. The first question asks you to write all the codes in the main file. And the second question asks you to write the codes in the main file and a separate function file, false position.m. So let's see how to do the first problem. We write all the codes in the main file, so we need to create a new script and clear the screen, clear all, close all. If you want to see more digits, you can format long. And let's save this file as main.m. Right. Then we need to create a function. Since we need to write all the codes in the main file, so we should not use a separate function file, right? So we need to define the function in the main file by using the @ symbol. So f equal to x to the power of 10 minus 1. And we start with the interval from 0 to 1.3, so a will be 0, and b will be 1.3, and the two epsilon constants are 1e negative 3. Epsilon abs also equal to 1e negative 3, all right? And then we can start the while loop like we did in the bisection method. And then instead of finding the midpoint, we need to find the intersection point C. We can directly use the formula for C, which is BFA minus AFB and over FA minus FB. So B times FA minus A times FB and over FA minus FB. All right, this will be the intersection point. Alternatively, you can define C as AFB minus BFA over FB minus FA. That will be the same. After you find the intersection point, remember that you will have 3 different scenarios. You can check your previous note. So the first scenario is that the intersection point C happens to be the root, which is very unlikely in practice, but it's possible, right? So FC equal to 0. And then we can stop the iteration process because we already find the root, which is C. So the root will be equal to C, and we can break. The second scenario is that FA and FC have opposite signs. Opposite signs means FA times FC is less than 0. If this scenario happens, we make a variable step equal to 1 minus C, and then make the value of C, assign the value of C to the variable B. So B is updated. Pay attention to this. If you make B equal to C first and then define step equal to B minus C, then the step will always be 0 because you just updated B to make it equal to C, right? So the order really matters. You need to first define the step and then make B equal to C, right? The third scenario, which is FB and FC have opposite signs. So if that happens, step equal to C minus A, and we can define, make the value of C equal to the variable A. So A is updated. And this is all the scenarios. Then we can end the while loop. So my question here is how to write condition for this while loop. Okay, so it's very similar to the bisection method. Let me show you here. Remember that the halting condition to stop the iteration is that condition A and condition B are both satisfied. To satisfy condition B, condition B1 or condition B2 needs to be satisfied. If this happens, then we can halt. But the condition we need to put in the while loop is the opposite of this halting condition, right? If the opposite of this condition happens, then we can continue. So the opposite of this condition will be A opposite, the opposite of A, or when you do the opposite, the AND become OR and OR become AND. Okay, so A opposite or the B opposite. The B opposite is the opposite of B1 and the opposite of B2. Okay, so if this happens, then we continue. So remember that A, condition A, is step less than epsilon step. So the opposite of condition A will be the variable step larger than or equal to epsilon step. The opposite of condition B1 will be the absolute value of FA larger than or equal to epsilon ABS. And the opposite of condition B2 will be the absolute value of FB larger than or equal to epsilon ABS. Okay, so let's write the condition for this while loop. So it should be the opposite of A, which is step larger than or equal to epsilon step, or ABS of FA larger than or equal to epsilon ABS, and ABS absolute value of FB larger than or equal to epsilon ABS. Okay, so this will be the while loop. And you can see we have a variable step in the while loop as the condition, as one of the conditions in the while loop. But this step isn't initialized, right? So we need to give this variable an initial value. When you give it an initial value, you need to be very careful because we want to make sure the while loop will be triggered. For example, if the step is less than epsilon step, then we never go into the while loop, right? So we want to make sure the initial value of step is larger than epsilon step. So we want to define step as epsilon step plus 1. Okay. All right. So here, the goal of this program is to find the value of the root, right? So here we only find the root due to condition 1. So if we halt due to condition 1, then the root will be equal to C. What if we halt due to condition 2, right? So we need to write here if the halting condition 2 is satisfied, right? Which is condition A and condition B are both satisfied. So condition is step less than epsilon step, and condition B. Condition B is satisfied when B1 or B2 is satisfied. So absolute value of FA is less than epsilon step, or the absolute value of FB is less than epsilon step. Okay. So this is if we halt due to halting condition 2, then we need to use A or B as the root, right? Depending on which one is a better approximation. So if the absolute value of FA is larger than the absolute value of FB, then B will be a better approximation for the root. So the root will be equal to B. And else, if the absolute value of FA is smaller than the absolute value of FB, then A will be a better approximation. All right, so we can end this if condition and end this if condition. So this will be the main file which implements the false position method. So let's run to see if there are any errors. Right, so root. Okay, so the exact root will be 1, but we have a tolerance 1e negative 3. So this solution is good enough for this application. All right, so before we talk about condition 2, let me ask you a question. What if we want to visualize the iteration process, right? Then we can know how we reached the root and how many iterations we go through before we reach the root, right? So it's actually very simple. We just need to add a few lines. So before we start the iteration, we can pull out the function, right? The function fx from A to B. So we define the x coordinates as a vector from A to B, right? It should be from A to B, assuming that we have an interval 0.01. Okay. Then the y will be fx. So here the x is no longer a scalar, right? It's a vector. So we need to change the definition of the function to x dou to the power of 10. Otherwise, there will be an error. So then we plot xy as we want to plot the function as blue lines, and then we can hold on because later we want to plot something else on the same figure. So we need to hold on. When we go into the loop, after each iteration, we want to visualize how the intersection point is obtained, right? So we want to plot a straight line connecting AFA and BFB. So there are only 2 points. So the x coordinate of the 2 points is A and B, right? The first point is AFA, the second point is BFB. So the x coordinate is AB, and the y coordinate for these 2 points is FA in FB. So these are just 2-element vector, which is enough for to plot a straight line. Then we plot x versus y, and we can use right line for the straight line. Then we can hold on. Okay, so after each iteration, we will plot a straight line. So if you want to see what happens before we goes to the next iteration, you can pause. So if you pause, you need to press the enter key to continue. So let me show you how this works. Okay, so here is the initial, is before we start the iteration. We have the function from A to B, which is from 0 to 1.3, and we have a straight line connecting AFA and BFB. So the intersection point with the x-axis, right, will be the next, will be this point C, right? Then we can start the next iteration, and this straight line connects AFA to BFB, right? So we can do this again and again and again until, so you can see the root is here is 1, right? The root is 1, so we are closer and closer to the root. But you can see for this function, the false position method is really slow because we have gone through so many iterations before we reach the root, right? So when the figure disappears, you find the root. All right, so this is how to visualize it. Let's see question 2. Write the codes in the main file and also create a separate function file for false position.m. So let's see how to do this. All right, so we need to create a function file, function, find the root by root, which is the output parameter, equal to false position. The input parameter will be the function f a b for the interval and the epsilon step and epsilon abs, right? Then we can save this as false position.m. So the main file, we can remove the general part, right? So after here, after we define the function, the initial interval, the 2 epsilon constants, then we can call the function file false position.m. So root will be equal to false position f a b epsilon step and epsilon abs, right? Then we can move, copy paste this part into the function file. All right. So this will be the false position, and let's see if there is any problem. So there is a plot inside the function, so you can visualize how we approach the root, right? Then after it disappears, it returns the root, right? So this is how to do question 2. And there is one more thing. So when we write the function file false position.m, we assume that the input parameters from the user are always valid. We assume that the user knows the initial requirement for the false position method. However, sometimes their input parameters may not be valid, right? So we can check if the input satisfies the initial requirement. For example, when the user inputs f, a, b, and fa and fb may not have opposite signs. If that happens, then we cannot find the root. So let me okay, there are other scenarios. For example, at the end point a or b, the function f is 0, right? For example, at the function f at a is 0, then we know that a will be the root. Then we don't need to do the false position method, but don't need to do the iteration, right? And also b can be the root as well. So let's check if f, a, and b, these 3 parameters satisfy the initial requirement. So if fa is equal to 0, then we directly find the root, right? The root is a. Else, if fb is 0, then we find the root, which is b, right? And also else if FA and FB do not have opposite sign, which means FA times FB larger than 0, then we can send a error message, right? Error which says that FA and FB do not have opposite sign, and then we can end. So if the user, we remove this, okay, if the user is aware of the initial requirement for false position method, we will never go into this if condition, right? But if some users are not aware of the initial requirement, if they put inappropriate parameters, then it will generate an error or directly find the root. All right, so let's try if we use to see if we can get the error message. So for example, we want to search the root from 1.3 to 1.4, right? Then we can run. So you can see there is an error message, FA and FB do not have opposite sign, which is exactly as we defined in our function file. Okay, this is the MATLAB coding, and of course there are many different ways to write the program. So you can write, you can code in your own way. I just provide one way to do it, and there are many different solutions. The solution is now unique for coding questions. And then let's talk about the quiz problem. Okay, so this will be quiz 3. It's the question 5.10 on page 148 on the textbook. So the problem is like this. Water is flowing in a trapezoidal channel at a rate of Q, which is equal to 20 meter cubic per second. The critical depth Y for such a channel must satisfy this equation. Okay? The parameter G is equal to 9.81 meter per second square, and AC is the cross-sectional area, and B is the width of the channel at the surface. For this case, the width and the cross-sectional area can be related to the depth Y by the following two equations. B is equal to 3 plus Y, and AC is equal to 3Y plus y squared over 2. And it asks you to solve the critical depth by using both the bisection method and the false position method. You need to start with the interval from 0.5 to 2.5 and assuming that epsilon step is equal to epsilon ABS and both of them are 0.001. So there are two questions, as you can see. The first question asks you to use bisection method to solve this problem. You need to write the codes in the main file and create a separate function file called bisection.m. And the second question asks you to use false position method. You need to write the codes in the main file and a separate function file, false position.m. This will be the end of the third class. In the next class, we will talk about another technique to find the root of nonlinear equations. That part of the knowledge is in chapter 6 of the textbook.